Hello friends, it's me again, Dr. Patterson. In this video I'm going to go over the topics for week 3, which is mainly introducing you to servos. I've already talked about potentiometers a little bit, but we'll go over them again and then look at how we can actually start making things move with some level of positional accuracy. We looked at DC motors last week. Now it's actually being able to move and either tell a position or a velocity at which we're moving at. There's ways to do it with DC motors as well. It's just servos are built essentially to be that like run that way. And they are very easy to control. And a lot of the circuitry needed to do that is integrated directly into the device. So we're have this flipped upside down. So where I've used some of these before in a lot of projects for potentiometers, you'll see these little tiny ones right here. These were essentially to allow us to set a reference voltage for the stepper motor drivers, and the reference voltage essentially tells the chip how much current to let through to go to the motors. We were also had been working on the use of servos for different purposes inside the 3D printers that we made. One was testing out essentially like cleaning off nozzles. We had a 3D scanning device built into it as well, and there was other things that we were exploring for changing lights and or camera position. So potentiometers, really simple, right? It's you put in 5 volts on one side, you put ground on the other side, and you measure voltage in the middle. And that's what I've got hooked up right here in the circuit is just potentiometer, 5 volts from the board over and then directly into one side, the top, and then ground coming over to the board and then wired into the bottom. And then I have this wire actually, instead of hooked up to the board, I have it hooked up to something called a oscilloscope, and I wanted to show you what that shows. We can actually look at what the voltage reading is on there without hooking it up to the board and taking a measurement. So you can see as I change this, we can look at the voltage changing that's measured at that particular pin. And so that's what the board is seeing when you're doing an analog read, and let's even do that. I need to, 1 second. There we go. I'm sure you all miss my face for this one. We'll do a clear all, close all, and then create a new connection to the Arduino object. We can say, or create a new Arduino object. And just use the Arduino command. Don't need any arguments. If you don't have a genuine Arduino board, you might need to specify which COM port or the type of board that you're using. And I am indeed waving my hands around like you can still see me. And then all we're going to do in here is we'll say tick and while true. We don't even need the timer. We'll just say while true. And essentially just over and over output what the voltage is that we're reading. So Arduino object, and I need to hook up a wire here. So not that one because it's ripped in half. Let's hook up a wire to that same pin and then go over to A0. Might get a little different signal while we're trying to read it and look at it on the oscilloscope, but it should be pretty much the same. So from that Arduino object, we want to say, hey, Arduino object, read voltage, and then we can pass it which pin, and we only need one argument for the read voltage, and we're getting back a value from this. And so we can say volts is equal to this. That's all we want to show. And let's put a small pause in there, say 0.1 seconds, just so we don't flood the command window. And then we can run this. And we should get a value right around what we're seeing on the oscilloscope. So like I said, we're getting a little extra noise because we're the Arduino complicates things, like the ADC that's involved does change the circuit essentially. So we might see a little more noise with both of these devices reading the same thing, because I don't currently all have everything grounded correctly. But we're just gonna go with it because it's just an example. So you can see as I go down on this, they're both decreasing and increasing, right? And then the other one that I want to show you is the pulse width modulation, which we'll get to in a second. But if we go back to the slides, so we now have a way to control, way to control a voltage output. And we can do that physically on using this potentiometer. Now servos are, we already did that. Servos use pulse width modulation to receive a signal, or like you send it from the board, the servo receives the signal and does something with that signal. It's not the same as the pulse width modulation we were using for the LEDs or the motor driver, because that was literally trying to directly correlate what was going from the Arduino to the physical device. In this case, we are sending the signal from the board to the servo and doing something a little different with it. So it's using pulse width modulation in that it cycles over and over and over, but instead of sending 0% duty cycle up to 100% duty cycle, the cycles are a specific width, and we're modifying the on time between two specific values so that we can have it sweep from, on the standard servo, -90 to +90 degrees, or on a continuous rotation servo, full speed in one direction all the way over to kind of halfway would be stationary and not moving, to the other side, which would be full speed in the other direction. So what's the difference, right? And we'll look at the signals in a second, but those servo motors, that there's a small microcontroller on there that's receiving the signal and processes it, and then uses at least for these cheap servos, uses a potentiometer to say, where am I? And then it is able to correctly essentially supply the voltage to the motor to make it continue to turn or try to turn or stop its motion. The gears on there, you can see, you can't really see them on your device, which looks kind of like that. But that white knob popping out of the top is indeed essentially all the same plastic for all those gears. Those gear teeth are very small. So if you try to make this thing lift too much, or you like hold it in place while it tries to go full bore in one direction for a long period of time, it can overheat and cause those gears to break. You can crank on the gears too hard, fairly easily, actually. Too hard in this case is like a mild amount of effort. And those gears will break, or just completely strip some of the teeth off there, and then they'll be unusable. The way that you can tell if it's functional or not, and I'm going to bust out one of these toppers for it, is, and during servo week, this is usually how I will test to see if a student's servo is broken. But if you, fresh out of the package, you should be able to hear it kind of like turn and make a noise. And I'm going to see if I can. If you do that, if you move it a little bit when it's powered off, make sure you don't have it powered when you do this. If you do this and the gears inside are broken, you will both feel and hear clicking noises, because the gears have either stripped and they're not working to meshing correctly, or the gears have broken and you're literally like mashing the parts even more. So don't try to, if it doesn't turn in one direction, don't try to keep turning it. It will break. It should move fairly easily back and forth. Don't try to grab the top part with the pliers or anything, because that there are tiny little teeth on there as well that fit right into the top, essentially the arms that go on there. So we can use these to control location or speed, or if for fancier servos, you can do go move to a position at specific speeds. High-end CNC or computer numerical control machines, like the some of the machining tools that we have in the lab, in the main lab at the science building, use high-end servo motors for all the motion. They'll even have servo motors for the spindle, which is what you normally put the tool into, and then it spins it really fast and cuts away metal. These are also, servo motors can also be used in 3D printers. Higher end 3D printers will use them as well. Using servos instead of stepper motors can be made much less expensively, because they effectively just, there's no requirement on having any kind of feedback. The high-end servos that are included in whether it's robotic arms or CNC machines, which you'll read about for next week, they have feedback loops, which either the circuitry that goes along with the motor will increase the power to the motor to try to get it to move exactly as specified, or it will tell you that it was unable to complete that move and you need to either stop the machine or address the issue in some way. So what we have is low-end version of that, which is it uses a potentiometer to try to move to a spot. So it will keep trying to move to a specific spot or at a specific speed unless you stop it, and in which case it will keep trying to, even if it breaks itself in the process. So we have the inexpensive, kind of dumb servos. So let's look at what those commands are. Well, for pulse width modulation, going back to the MATLAB version, let me stop this because this has been reading a voltage that entire time. We want to, let's think about this. We want to write a PWM signal. And I'd like to show it to you on the oscilloscope. So what's one way that we can do that? We could start a timer and then say while TOC is less than 20. Let's, inside here, let's say we would just want to run tell the Arduino object to, hey, write PWM voltage. And we're going from 0 to 20 seconds, so we can say TOC divided by 4. And that'll get us a value, the PWM voltage, between 0 and 5. The only thing I forgot to do here was I need to specify pin. And if you look at the board, I have, if I move this over just a hair, I've got a wire plugged in over here, and it's wired into D6 again. So we'll go with D6. So pin first in either character or string form, which try to always stick with the string form. D6, and then a value, the voltage that you want to write to it. So let's do this, and then let me just hook up this to PWM signal instead. And what we should see right away, yep, that essentially drops to 0. It's reading very low millivolts right now, so thousandths of a volt. So if we write this now, we should see a voltage that we're going to range from 0 to 5 volts. So if I click run on this, not twice like I just did, let's see what happens. Let's kill that real quick. Okay. So let me hit a couple buttons on here. I'm going to have it automatically adjust the scale so we can see that pulse width modulation signal. So what you're seeing here, let me back that up. Or you know what would be even better is if I had control of this signal. So let's, instead of this talk divided by 4, let's say Arduino object dot read voltage and pass it A0. So I can use the potentiometer to control that PWM signal. And then let's run this again. So you can see as I drive that voltage lower, we're getting less on time during that set cycle. And that cycle is repeating over and over and over again, right? And as I go all the way up towards 5, we're essentially just getting 100% on. And it stopped, so I need to, let me change this to true. Run that again. Yeah, so I can dial it up or down and use that voltage to set the PWM signal. So that's just PWM. Now, if we want to control a servo, it actually uses kind of the information in the PWM signal to set a position on the device. So what I'm going to do instead of, and I need to stop my code. Maybe, there we go. Instead of writing a PWM signal, I'm going to create a new object. And that new object is going to be, we'll say let's say servo object. And what we need to pass it is, and let's pull this up. So heading over to documentation and just look up if my internet works. Creating a connection to the servo. This is for Raspberry Pi, which is not at all what I want. Arduino hardware, there we go. So we need to pass it 2 arguments here. One is, they say A, which is their generic version of an Arduino object. That's the variable they always use. And then pin, which is any one of those PWM capable pins. So I'm using D6 right now, but it's 3, 5, 6, 9, 10, and 11. So we can use any of those, and we will for the simulator that I've built. So we can say for the servo object in this case, we want to create a new servo, and we're going to pass it the Arduino object as the first argument. And then we also want to specify pin D6. Oops. And then now we've got a servo object. Let's go back. Now, what do we do with this, right? We don't use write PWM voltage. What we have is a new set of functions or methods in this case on, it's like part of the servo. And so we need to say, hey, instead of saying, hey, Arduino, we're saying, hey, servo, write this position. And the position, let's start with write. The position ranges from 0 to 1. And so we need to say, just like we were doing for the Arduino, hey object, do this action. And so we can say, hey servo, write this position. So let's do that. Let's keep that there. Let's say servo object. I'll even cut it out so this makes a little more sense. So hey servo object, write position. And then I need to just pass it 1 argument because it was created with a specific pin in mind. And it holds on to that value. You don't need to specify the pin again because it is an object that is specifically directed at that particular digital pin. And so we're saying, hey object or servo object, we need to move you to this position. And all we need to do is specify that position, and it is a value between 0 and 1. 0 is going to be negative 90 degrees, 1 is going to be 90 degrees, or depends on your servo and all that good stuff. So we can specify a value there. Well, we've got something where we're reading a value between 0 and 5, which is read voltage, and we can just divide it by 5 in this case. So we're now going to write that that read voltage value, the 0 to 5 volts from the potentiometer to the servo. So let's give that a try. And the servo is not going to move because I haven't wired it up yet. But we are going to look at, let me hit the auto button again. We get a better view of this signal. There we go. You know, it's so far zoomed out that it's not great. So let's try. So this, I'm going to go all the way to 0. And you'll be able to see it doesn't go, let me zoom in again. It doesn't go to 0. It goes to a minimum value. Right? And then if we wanted to zoom out a little bit, now I'm going to go to a maximum. It doesn't go to 100% on. It goes to a slightly larger value. So I believe, if I remember correctly, you've got roughly, oh geez, 1 millisecond? No, that's not right. Well, now I'm going to look it up. 1 second. Should have trusted myself.
I'm so excited about what I'm.
Have that page open for you guys somewhere, and then start it up. It totally is 1 millisecond range, but the total kind of cycle time, that's the one I was blanking on, is 20 milliseconds. So when we go all the way down to 0 here, we're seeing a pulse width that's 1 millisecond. So 1/20th of that total cycle. And then when I go full on or full to the other side for the servo, we're seeing the pulse width of 2 milliseconds, so roughly 10% of that total cycle. So it's not, it uses pulse width modulation, but it's not the actual pulse width percentage of total on time that's important. It's that difference between the 1 millisecond and 2 millisecond on time for that 20 millisecond cycle. Those specific numbers can vary between servos. Most of them are between 1 and 2 milliseconds in length. Some with limited range might have shorter bands, essentially, just so I think they do it so it makes more sense for what's fairly standard from that 1 to 2 milliseconds. But yeah, make sure when you get a servo, if it's not one of these made 10,000 at a time kind of servos, you might want to check the data sheet and make sure you're sending the right signal length and on off time for that, because you can set those values in both in MATLAB and also in C, C++ for Arduino, and also in Python. Feel like I'm missing something, but I'm pretty sure that's everything. So servos, I'm going to pause and I'm going to show you the servo move. 1 second. All right. So I've got the potentiometer hooked up, the servo hooked up, and I'm still running that same code. And so all I'm doing is changing the position of the potentiometer, and the servo moves along with it. All the way from one side, which is this is all the way, to it should move 180 degrees, yep, to the other side. With these servos, especially as you get a little larger servos that you can still hook up to the Arduino, you just start noticing more noise. There's noise in the potentiometer signal that you can read. Some potentiometers will have more result in more noise in your signal than others. And that can end up, if you're writing it directly to the servo, end up causing it to like jitter. You may or may not be able to hear it right now, but it's like kind of like jittering a little bit. And that's kind of expected with some of these because at least these low end ones, it's using, like we're using a potentiometer, reading the values and writing those to the servo, and then it's essentially using the same system, a potentiometer, to make sure that it's in the right position. And so there's a lot of room for noise to be introduced into this very inexpensive positioning device. So that's all I've got for this one. I'll be back after this with a wiring video, which we're going to end up making something very similar to this, just without the oscilloscope. See you in that one.